Hello, everyone. I'm Satish. I'm here on behalf of the young researchers team of the International Society for Quantum Gravity. And today we are very excited to have Giulia talk about quantum gravity phenomenology. It's a recently new area and burgeoning. There's a lot of work going on, and probably this may turn out to be more prominent than other areas of quantum gravity because it's we are connecting to experiments, right? And she will be giving a set of three lectures, and today is the first one. Enjoy the lecture. Thank you, Julia, for accepting our invitation, and go ahead.
Thank you for the introduction and thank you for inviting me to give these lectures. I'm very excited about them. So it's going to be three lectures about quantum gravity phenomenology. As you mentioned, this is not a very old field. It's, say, roughly 30 years old now, if we want to be generous. So there isn't really a canon within it. There are many different approaches, many different lines of research. And what I am going to do, especially in this first lecture today, is try and give you a bit of a feel of why this field is here. First of all, why it is important within the search for quantum gravity, and also how does it work? What is the underlying idea behind it? And then in the next lectures, which is tomorrow and next week, I will go a bit more in detail about actual experimental tests that people are considering. So the plan, oops, this is not advancing. Let me see. Yes, now it's advancing. So the plan for the lecture today is a brief introduction about the quantum gravity problem framed from the point of view of someone who is interested in phenomenology. Then a discussion about what is the scale of quantum gravity, since we need to know where we are looking for something. I will say a few words about what is quantum gravity phenomenology, as I said, and then I will give a couple of examples about how we can model properties of quantum space-time with the goal of doing phenomenology with them. So one example concerns space-time noncommutativity. Using this model, I will also start discussing the issue of symmetries, space-time symmetries, relativistic symmetries in quantum gravity. I am doing it today because having discussed that model is helpful in seeing some things in how can they work in a specific model in practice. And then I will also discuss another example of modeling of quantum spacetime properties, which is running of spacetime dimensions. So today there's not going to be discussion about actual experiments. I want to set the ground, and then this is experiments or observations are going to appear from tomorrow onwards. Okay, let me start. So first, a little bit of a prologue. Since we are doing something really new, it's useful to see how things were done in the past, because maybe there is some interesting lesson to learn there. So you know that at the beginning of the 20th century, we had a lot of progress in physics. In particular, there were two big revolutions. One was the birth of special relativity and general relativity, and the other one was the birth of quantum mechanics. So basically, it's when the two main pillars of our current description of nature were born. And how were these theory devised? So concerning special and general relativity, you know that they were developed in a relatively short amount of time. So by the by the first 20 years of the century, they were basically fully described. Then, of course, people have been studying consequences and details in much more detail, but they were already fully established. And the motivation for them were a combination of experimental observations and theoretical arguments. So first of all, special relativity was born because there was an issue about speed of light as predicted by electromagnetism and invariance by change of reference frame. And at the time, change of reference frame was done according to Galilean relativity, which was the relativity theory of the time. Once it was experimentally understood that this speed of light was in fact invariant with respect to the state of motion of observers, so the famous, for example, Michelson and Morley experiment, then people started to think about how this invariance of the speed of light could be compatible with the relativistic transformations, and Einstein famously came up with the theory of special relativity, whose invariance of the speed of light under change of inertial reference frames is one of the main pillars. Once this was established, then it was another conceptual. So the birth of special relativity is already a mix of observations and conceptual considerations. And once special relativity was established, then it was understood, first of all, at the conceptual level, that special relativity was not compatible with the instantaneous propagation of the Newtonian interaction. So this was a theoretical problem. But also at the time, there were already experimental problems with the Newtonian gravity theory, because people had been observing the Mercury's perihelion precession, and the behavior of these was not in agreement with the predictions of Newtonian gravity. So, well, they had tried to fix this by adding one planet to the solar system, hoping that that would solve the problem. Didn't work. So, well, eventually general relativity was developed. It took some 10 years, but it came out as a complete theory. On the other hand, the birth of quantum mechanics was much more chaotic, let's say. So it didn't start with the conceptual problems. So at the conceptual level, there was no real need to introduce it. However, between the end of the 19th century and the beginning of the 20th century, a number of observations started to emerge that people could not describe within the standard classical theory. And the famous examples are the photoelectric effect, black body radiation, the stability of atoms, and several others. I'm not going to list them, otherwise it's 2 hours just talking about the birth of quantum mechanics. So quantum mechanics was really born out of experimental pressure, let's say. There were experiments and people needed to explain them. And in fact, it was not born as a complete theory, let's say. So a full theory of quantum mechanics took, say, 30 years to be developed. At the beginning, people were only devising phenomenological formulas that could explain observations. They started seeing that these formulas they were devising were pointing in the same direction, namely quantization. And from there, then people started to build the full theory. So in some sense, we can say that the development of the relativity theory was a revolution, but it was somehow an orderly revolution. So it didn't really require to introduce radically new concepts. I mean, it introduced radically new ideas, namely the dynamical properties of space and time, but it was based on pillars of known physics. Space and time were already there. They only had to be assigned new properties, let's say. And a signature of this fact is that the laws of the relativity theory admit, straightforward, smooth limits to the Newtonian and Galilean theories. For example, if you look at the law to some velocity in special relativity, consider, do you see the arrow if I move it? Yes.
Yes, I can see.
Very good. So I was saying, if you consider how two velocities that are collinear are added up in special relativity, this is a famous formula, you all know it. You straightforwardly take the limit in which the two velocities are much smaller than the speed of light, and you get the law of addition of velocities of Galilean relativity. So you see, this is a smooth limit, meaning that you know which parameters have to be small in order to get what you had in the previous theories. So in some sense, you can think about the relativity theory as an extension of what was already known. I mean, a revolutionary extension, but still that. On the other hand, the quantum theory was a more radical kind of revolution, we could say, because it really required to revisit the foundations of classical physics. It needed to introduce new concepts such as probability, quantization. These were things that were not there in the previous theories. When people were developing it, they were so shocked that at some point they were, to explain the stability of atoms, at some point they were even considering abandoning conservation of energy. They were ready to abandon everything once they understood what they were getting into. Okay, it was really, it must have been shocking to be there at the time. And a signature of this, of how radical the quantum theory is, radically new with respect to the previous theories, is that some of its formulas, so for example, the phenomenological formulas that were written in what is now called the old quantum theory, so the one that was developed in the first 20 years to explain observations, they have no straightforward limit to semi-classical physics. For example, if you consider the formula for the energy of electrons in the photoelectric effect, that is related to the frequency of light that is hitting on the metallic surface and then emits the electron, then you have a formula related to the energy of the electron to the frequency of light, and then to some, this is called the work energy needed to extract the electron from the atom. This formula doesn't really have a limit, a corresponding limit in classical physics. So it's a formula that you would not have written within classical physics, not even in an approximate way. While here you have that in the previous theoretical framework, you would still write a formula that is an approximation of the more general formula, okay? And this helps us in thinking about quantum gravity. So we don't know whether quantum gravity is going to be a somewhat orderly revolution or a radical revolution. In principle, we have to be ready for any of the options. In the second option, the radical revolution, in that case, we really need some experimental guidance. The quantum theory would not have been devised, would not have been even dreamed without some experimental guidance. We do have, and I will discuss this in a bit, we do have conceptual arguments while for saying that we expect that something happens in a quantum gravity theory, something new. But we really don't know what it is. And if we expect a radical revolution, then just the conceptual arguments will only bring us up to some point. Then at some point we will need guidance from nature. And yeah, as I was saying, we do have theoretical arguments for a need of a theory that describes the scales where we have quantum and gravitational phenomena together, so none of them is negligible. And we do have very experimental results. I find very interesting to look at this writing by Chris Isham in 1995, so just a bit more than 30 years ago. And he was talking at the GR14 conference and was talking about the status of quantum gravity research at the time. And at the time, quantum gravity research was purely theoretical. They had been done a lot of work to develop theories of quantum gravity, and they had already started most of the main theoretical avenues that are studied today. And Chris Isham was wondering about what are the basic structures that this theory would need. And interestingly, he asks, how iconoclastic do we have to be to construct a full theory of quantum gravity, which is equivalent to what I was saying, how revolutionary do we need to be? And then, I mean, at the time, phenomenology of quantum gravity was not a phrase. People were not really using it. In fact, the field of phenomenology of quantum gravity was born in the late 90s, let's say, in a more structured way. Before that, people, yes, they were thinking about possible signatures of quantum gravity, but mainly they thought about, I mean, they were thinking that the scale was so far away from us that it would be impossible to see anything. And he goes on to say the key problem is to identify the correct choice of such building blocks among the myriad of possibilities. He mentions that certain broad ideas are suggested by existing research programs, and this is something I will come back several times during my lectures. And then this is the very end of his talk. This is the proceedings of the talk. So this is the very end of the article. You can find it on arXiv. And he goes on to say, on the other hand, it is possible that none of the current programs is on the right track, in which case we need to look elsewhere for hints on how to proceed. What is missing, of course, is any hard empirical data that would enforce a fundamental shift in approach, which brings us back to a question raised at the very beginning of the paper. Is it possible to find experimental tests to resolve some of the many obscure issues that cloud the subject of quantum gravity? In the beginning, he had started on a very negative perspective about this. He was saying we cannot do it. But then, I mean, here I'm not reporting everything. He mentions a few considerations, and then this is the very last sentence of the paper. So the situation concerning experimental tests is not completely hopeless, but it is something we must continually strive to improve if studies in quantum gravity are not to become the 20th century equivalent of the medieval penchant for computing the cardinality of angels on pinheads, an ever-present danger at this extreme edge of modern theoretical physics. So he was warning people that conceptual and theoretical consistency, they are very important guidances. However, at some point, you do need to compare somehow to nature. Otherwise, it's really hard you're to argue that you're really talking about a theory of nature and not some metaphysical, let's say, model. And Well, luckily, I mean, he was not. He was hoping for this. He was not very optimistic, but luckily things have changed since his talk. And we are going to see how in the course of these lectures. So now let me start with what are the important what kind of conceptual guidance we have also in devising phenomenological perspectives for quantum gravity. And let's see what is the problem in putting together general relativity and quantum mechanics. So we know that general relativity concerns macroscopic bodies, and it is based on a dynamical spacetime on which classical matter moves. Well, in fact, classical matter and the dynamical spacetime interact according to Einstein's equation, and they influence each other. On the other hand, we have quantum mechanics that concerns the microscopic world. For quantum mechanics, space-time is a fixed stationary background, and matter has quantum properties. So we have dynamics of matter that is not influenced by space-time. Space-time is, well, basically is flat space-time. Then, yes, we have extensions of quantum field theory on curved space-time, but even that has problems. In any case, there is no dynamics for space-time. And you already see here that the two theories are really fundamentally different, and you already see that it can be hard to put together, say, quantum matter on a dynamical space-time. And you can see this in a more quantitative way, even though still based on relative heuristic arguments. When you think about how the two theories localize points or test particles. So for general relativity, you need test particles that have low mass because you want to minimize their back reaction on the geometry. On the other hand, in quantum mechanics, you want probes that have high mass because you want to minimize the quantum uncertainty if you want to use them to localize a point. In general relativity, the localization limits can be understood when thinking about the Schwarzschild radius, which basically predicts what is the limit. Well, it gives you the scale, the limit for squeezing a mass m into a small region of space-time. If you want to put too high a mass in a too small region of space-time, then you will create a horizon. And the Schwarzschild radius tells you what is the mass that you can put within a radius before creating a black hole. On the other hand, in quantum mechanics, you can have a rough limit in localization by looking at the Compton radius, which tells you what is when is it that you will impart so much energy on your probe. So to test the position of a probe, you have to send a signal, say light, of higher and higher energy, so shorter and shorter wavelength to have a better precision in your measurement. However, if you send a photon with too much energy, then you will start having particle creation. Okay, so you will not be sure any longer about what particle's position you are measuring. And this is given by the Compton radius. And you see that the Schwarzschild radius decreases with decreasing mass. And on the other hand, the Compton radius decreases with increasing mass of your probe, okay? So at some point, you will not be able to localize things neither in GR, neither in GR, neither in quantum mechanics. So when the two scales become the same. This is kind of a heuristic argument, but it tells us that, yes, we should expect that within quantum gravity, the very nature of spacetime and also the concept of localization are probably going to be affected. And in fact, this was already understood in the 30s, which is when the research about quantum gravity was born. So really shortly after the birth of general relativity and quantum mechanics. And at the time, people like Landau, Peirce, Bohr, and Rosenfeld, they were studying how to measure the electromagnetic field and what are the limitations to this measurement due to quantum effects. They came to the conclusion that you can measure accurately the electromagnetic field if you send the ratio between, if you basically send the charge of the field to zero, let's say, which maybe not physical, but it is consistent within the theory that you're studying. And then in the late 30s, Bronstein tried to use similar arguments applied to the gravitational field, again, to see what would be the quantum limitations, so the limitations due to quantum features to measuring the gravitational field. And similarly to what had been found for the electromagnetic field, he found that to have a good localization, you would need to send the charge, the gravitational charge of the particle to zero, which is the mass. Well, but in fact, what had to be sent to zero was the ratio between the charge and the mass. So in this case, it's the ratio basically between the inertial mass and I'm missing a word at the moment, but okay, I think you understood. So because the charge, the gravitational charge is the mass, and this is not possible. So it is not possible within the theory to have an optimal localization of the gravitational field. So yes, this is something that we should expect. And now the question is, where should we expect to see these signals of breakdown of localization in some sense? Or where shall we expect to have a breakdown of our current notion of spacetime, either in GR or in quantum mechanics? And you probably have seen already this plot. Here there is length scales, mass scales. And basically this line is the one given by the Compton radius, and this line is the one given by the Schwarzschild radius, okay? And whatever is on the colored side of the plot is something that cannot be described either within quantum mechanics or with general relativity. And everything we can describe is in this triangle in the upper part of the plot. Everything we can describe with either one of the theories. But usually one is the one that dominates, so it's either one or the other. And then you see that these two lines meet at the point, and this point is found by setting equal the Schwarzschild radius and the Compton radius. And unsurprisingly, this is the Planck scale. Okay, so in terms of mass scale, it's well, it's the one combination of the fundamental constants that has the dimension of a mass. The Planck length is the one combination of the fundamental constants that has a physical dimension of a length. And you see that they are either a very large mass scale, well, compared to typical scales of quantum objects. And it is a very tiny length scale. Now, here, before we go on, it's important to keep in mind that we got to this point by making some important assumptions, namely that the laws of quantum mechanics, the ones that of relativistic quantum mechanics, the ones that lead us to define the Compton radius, and also the laws of general relativity that lead us to define the Schwarzschild radius, still hold up to this scale. This is not necessarily true, okay? So this is already some assumption. Well, it's not an assumption. It's a heuristic argument that helps us in developing an intuition, okay? But we are really making a big inference, assuming that we have no reason to expect that there is no modification.
May I ask a very small question?
Sure.
Is this because on the, for example, large scale end of things, like close to the sun and like these very large distance scales, that you can have perhaps different IR theories of gravity? And if you say that, okay, maybe to explain, I don't know, some galaxy curves or whatever, I'm using some Horndeski theory and whatnot, that maybe that influences where this intersection lies. Like if I'm using a different theory than GR, for example, for
well, so here where this area, where this region is influenced by the short distance properties of gravity. So at the moment, we know that gravity works roughly up to 10 to the minus 6 meters, which is somewhere here. Okay, we have no idea about how gravity works down here. It may be that the kind of modification of gravity that we may have at some point when we have a quantum theory of gravity has both an influence on the infrared properties and on the, let me call these the ultraviolet properties, but it is not given. I mean, if we take at face value only the infrared modification, then that affects what lies out of this plot here on the right. It might be that there is a same mechanism that changes this and also changes this. We don't know. Okay, so this is one of the many things we don't know. But here, at least at face value, what is relevant is the ultraviolet properties of gravity.
Thank you.
And well, since in fact your question helps me in going forward to the next slide. Because, for example, I mean, one very immediate example, I mean, of what could change the quantum gravity scale, putting it away from the Planck scale, is the fact that, for example, the Planck mass may run with energy, okay? For example, this has been already found in ground unified theories. Then you may consider them as a good description of nature or not. I mean, at the moment, we don't know, but it is one example of a theory where we have a running of the Planck mass, okay? So we can expect in principle that this happens also in other theories. There is the famous argument, again made within ground unified theories, that the couplings of the various forces that we have may run to a same value, and this may happen around the Planck scale. Of course, we don't really know, again, because we would be making an inference about how these forces behave at scales that we have not experimentally tested. There are, but something that has been found is that if you include effects of gravity within an effective field theory framework, for example, to study the running of standard model couplings, then the scale where unification may happen changes. So we do know that gravity and quantum field theory, which is the modern realization of quantum theory, we do know that they affect each other. Okay. Again, this is based on specific theories, but as I was saying in the beginning, it is useful to see what the theories that we have developed have to say, because it gives us hints about what may happen. Okay, so it's useful to account for these, say, theoretical hints. Let's call them this way. At some point, we would like to have experimental hints, but theoretical hints are already good. And then, it has also been shown in asymptotically safe gravity that the Newton constant runs. So this also may change the actual scale of quantum gravity, okay? So in general, when you do phenomenology, you do set the Planck scale as your benchmark, but you are also aware that you may be off by a few orders of magnitude, okay? In some ground unified theories, some people have been saying that you could be off by many orders of magnitude, but okay, that's extreme. But by the least, we should be ready to have a quantum gravity scale that is few orders of magnitude away from the Planck scale that we usually write. And this said, so the Planck scale, as you have seen, is tiny in terms of length. And this is interesting because it shows you that if you count the orders of magnitude, the size of a cell is as far away from the Planck length as it is far away from the size of the universe. Okay. So trying to guess what is the structure of space-time at the Planck scale based on, say, what we know about particles from LHC is as trying to guess the structure of the whole universe by just looking at the motion of the planets. Okay, it would be really hard. Okay, or trying to guess what is the motion of the planets based on what you know about the behavior of cells. Okay, it is really a big leap in in imagination. Okay, and this is why for many, many years, quantum gravity research was just theoretical. People were trying to do their best in using all the conceptual and theoretical arguments they had to go forward. And you have had also several lectures within this series, well, this year and also last year, and you heard about many different approaches to quantum gravity. As I was saying, from the point of view of phenomenology, it is interesting to look at what these approaches have to say, because maybe there are some recurring features, and then you may want to see if there is a way to test them, or they can give you ideas about what to expect. Okay. So it is really, ideally, these two sides, the theoretical side and the phenomenological side, should really work together to try and make progress. And here, this is just a little preview about what is coming in the next lectures. I was saying that now we talk about quantum gravity phenomenology. Why did we start doing that? It was not just out of desperation. There is also desperation, but it is mainly because people have started to realize that there are frameworks where one could see quantum gravity effects without necessarily producing Planck scale, Planck energy particles, okay? Or without necessarily going close to a black hole of Planckian size. And some ideas that have emerged concern, well, the fact that when you look at signals from astrophysical sources, they travel for a very long time. And if they travel in a quantum space-time, you may see accumulation of these effects, a little bit like what happens in the Brownian motion, okay? You deduce the molecular nature of water because you see the motion of little grains of dirt moving on it. Then we have cosmology. So we know that, well, we have good reasons to believe that in the very early universe, the relevant scales were Planckian. For example, perturbations had Planckian wavelength. And the universe expands, so it stretches these Planckian scales to large scales over the expansion. And those scales correspond to macroscopic scales today, and we can observe them. For example, we observe imprints of primordial perturbations in the cosmic microwave background. So it is like using a microscope, right? You you zoom in and you see this very small scale. And then there is also even more recent advance concerning the fact that experiments studying quantum systems in the lab are becoming very precise nowadays. So much so that in the last, say, 10 years, people have started to be optimistic about the fact, about the possibility of looking for the interplay between gravity and quantum systems using experiments done in the lab. So in this case, what is helping is the technological improvement, okay? And this is something that, I mean, this is something a bit more recent. Well, it's old and recent at the same time. And this is something that I will discuss at the end of this mini course. Well, I don't want to spend much more time on this, but yeah, so this is what I've been getting at so far. So how do you want to do, how does this phenomenology work? So it's really hard to test directly a prediction of a fundamental theory because these theories are hard. So it is hard to make a prediction for the actual outcome of an experiment. However, these theories do give us inspiration about features that we may expect to see. Okay, so we can build some effective models that do not aspire to be a fundamental theory of quantum gravity, but that are manageable when we want to compare to experiments. At the same time, we have to understand how these effective models relate to more fundamental theories, okay? But we can use them to model different properties of quantum spacetime, let's say, and test them, and inform, in turn, the development of the theoretical research. And a last remark I want to make before going to showing some more concrete, some concrete examples of these models, is the fact that, okay, we said that testing quantum gravity directly is hard. So here we have the cube of theories of nature, let's say. Each side is related to one of the fundamental constants. So for example, here you turn on the speed of light and you go from the Galilean theory to special relativity. You turn on H bar and from special relativity you go to quantum field theory. Or you turn on G, Newton's constant, and you go from special relativity to general relativity. Okay, then quantum gravity is in this corner where you have all three constants relevant. And the effective models that one can try and test experimentally they do not refer necessarily to this corner. In fact, they will, in most cases, they do not refer to this corner, but they refer to somewhere on the faces of the cube, right? For example, you may want to test deviations from special relativity. That means that you are testing a possible limit of quantum gravity going in the direction of special relativity. So if you get some information about this, then you will know about how the limit of quantum gravity in this direction should look like, okay? Another example is you may want to test deviations from standard quantum mechanics due to interaction with gravity. And in that case, you would be testing a specific limit of quantum gravity that is going towards quantum mechanics. And if you get some information here, then you will have another piece of your puzzle. So you will know how your theory behaves in this limit. You will know how your theory behaves on this limit. When I say you will know how, means that either you will have constrained some effects, or in the best case scenario, you will have discovered some effects, has not happened yet, in case you haven't noticed. And putting all this information together, you may start building a theory. Probably, I mean, if doing it in this way, it's a bit like the way quantum mechanics was developed, right? So looking at very specific effect and understanding specific effective phenomenological models that worked in that regime. And then in that case, the story ended well because then people were able to put everything together and construct the full theory. In this case, we don't know because we are not there yet, okay? Okay, so I mentioned that I wanted to discuss a few ways to model possible properties of quantum spacetime. One of them is noncommutative spacetime. Why it is interesting? Well, interestingly, again, in the 30s, the possibility that spacetime coordinates do not commute was proposed as a way to cure divergences in quantum field theory. Then people understood renormalization, and then this was not needed any longer, but it was one of the options on the table. But then the idea was revived in the 90s because, as I said, we have good reasons to expect that something happens to localizability at the Planck scale. We don't know exactly what. And having non-commutative spacetime coordinates is a way to encode the fact that there is a fundamental limitation in how well you can pinpoint a spacetime point, okay? Just because from a non-trivial commutator, you infer an uncertainty relation, just the way you do in quantum mechanics. And this can be anything. If you really want this to have something to do with the Planck scale, then it is reasonable to expect that in this object here, theta mu nu, the Planck scale appears. And you can imagine about having some first order and second order correction to the commutator. So a very general parameterization could be this one. And as I said, it is important also to have always an eye about what fundamental theories of quantum gravity tell us. And it is interesting that spacetime non-commutativity does emerge in some limits of some theories. So it is not unreasonable to think about it. For example, it emerges when you do string theory with the background fields. And in that case, the non-commutativity is given by your background field. There are results in loop quantum gravity showing that if you take in the flat spacetime limit in a certain way, then matter behaves as if it was living on a non-commutative spacetime. And also, if you do matter coupled to 2+1 quantum gravity, you do find again, and you integrate away gravitational degrees of freedom, then again, you find that matter has properties, the properties that it would have if you described it within a non-commutative spacetime. So now the question is, okay, I give you this commutator, and what do you do with it at the level of modeling? Okay. One slide aside, just to set the language. So let's consider quantum particles in a standard commutative spacetime. Then you can describe a free particle as a momentum eigenstate. That is the usual thing. And then you represent these momentum eigenstates as plane waves by projecting on the coordinate. Multiparticle states are given by the tensor product on the Hilbert space. And then you can represent your translation generator. Well, on one particle, it's trivial. On the two particle, the representation is just given by the Leibniz rule, okay? Which means that you take the translation generator acting on the first particle, and then you take the translation generator acting on the second particle. One formal way to call this fact, the fact that the translation generator acts by a Leibniz rule, is by saying that translations have a trivial coproduct map. So it's the coproduct map basically tells you the action on multiparticle states. And I'm introducing a terminology that will be useful in a second. And similarly, you can look at the representation of the translation generator on the dual space. And well, this is as usual the minus the momentum, okay? And you can call this fact as, you can say that this is given by something that is called the antipode map. So it's the action of the translation generator on the dual space, okay? This is just another language to describe the usual story. But this language is useful if we want to do non-commutative spacetime, because then what happens? It happens that if a particle on a non-commutative spacetime can still be described as a plane wave. However, this plane wave is not the usual commutative exponential, because now coordinates are non-commutative, okay? So it becomes a non-commutative object. And this means that you need to give an ordering. So you need to say this sum in which order is performed, because it would not be equivalent if you change the order. Moreover, if you consider the action of the translation generator on the one particle state, now you have that the eigenstate K is not an element of a vector space as it was before, but it is an element of a non-commutative Lie group, non-abelian Lie group. Again, because it has to be compatible with this non-commutative exponential form of the wave function, of the plane wave. Okay. So instead of having vector spaces, vectors labeling your momentum coordinates, now you have that K is the coordinate on the group of translation. And in turn, well, here the mathematics is very rich. I'm just trying to give you an idea about where it comes from physically. So what interpretation you give to the mathematics. These group coordinates, since they belong to a non-abelian group, then their composition law is non-commutative, meaning that the composition of G and H is different from the composition of H and G. And this means that now the coproduct of the translation generator P, when it is acting on a multiparticle state, say a two-particle state, does not obey the Leibniz rule as usual, but it obeys this deformed rule. Okay, earlier we had just G plus H, and now we have the coordinate referring to G summed in a deformed way to the coordinate referring to H. And similarly, you have a deformed action on the dual space, okay? Now, when these structures, the coproduct, the antipode are non-trivial, they form a Hopf algebra, no longer a Lie algebra. So earlier translations were given by a Lie algebra. Now they are given by a Hopf algebra. Why I am mentioning this? Because it is exactly this Hopf algebra structure that gives us the symmetry group of non-commutative spacetimes, okay? Then which specific symmetry group you have depends on the specific form of non-commutativity. Here I'm going to discuss one example. So the example in which we take only the linear correction to the linear contribution to the commutator, and a specific one such that the time coordinate does not commute with space coordinates, but space coordinates commute among themselves. I am considering this one because it is one of the most studied models within quantum gravity research, and also because it has a lot of structure. So it allows me to show you many different features. But there is, in principle, no reason to say that this specific example is better than any other. It's just useful for, for what I want to discuss. So we said that, of course, if you look at this, if you want to keep a relativity principle, meaning you want different observers to describe the same spacetime, as in special relativity, then you will easily convince yourself that this object is not covariant under the standard Poincaré transformations, okay? Which is something that you would like to have. The solution to the problem is that, in fact, you have to deform the Poincaré transformations, and you have to deform them exactly in the way that I was saying. So you go from having a Lie algebra for the generators of the Poincaré transformations to a Hopf algebra of the generators. And in particular, this means that the algebra, so the commutators, are deformed with respect to the ones of the Poincaré algebra, and in particular, you see here they are nonlinear. So this is a clear signature that you're going beyond the standard Lie algebra description. Given an algebra, it's always interesting to look for the Casimir, so for the invariant combination of the generators. And you see, usually this would be just P0 square minus P1 square in the standard Poincaré algebra. Here it is a nonlinear function. And then you have this non-trivial coproduct and antipode that I talked about before, which basically means that you have a deformed action on multiparticle states of the generators. Okay, now we want to make one more step towards possible observations. Okay, I'm not going to go to observations today, but I want to go as close as possible within this specific model. It is a way to also show what is the path that one wants to follow, regardless of what model one is starting from. Okay, you want to start from a model that has reasonable theoretical and conceptual grounds, and you want to see where it leads you, okay? And you want to do it in as rigorous way as possible, because then when you make predictions using that model, if you have a negative result, you will be able to say that the model is excluded. If you're not rigorous in your derivation, then if you get a negative result, this will tell you nothing about the model you started from, okay? Because the links that you use to go from the model to the prediction are loose. And this is a bit the problem that we have when we want to use the full quantum gravity theories, that at the moment, when we try to make predictions, we have to always, we cannot do it rigorously at the moment. It's difficult, okay? And this means that it is difficult then to assess what is the meaning of any observation for the theory we started from. So the reason for using simpler effective models is that at least the links are, that chain of links is as strong as possible, and then one tries to find the link to more fundamental theories. Okay, so let's start going in this direction. And for example, we may want to ask, what are implications for kinematics of particles of this model, okay? Kinematics of classical particles, let's say, the ones that we may observe with the telescopes, okay, not the ones we observe in a lab with a microscope. In that case, we are in a regime where h bar is going to 0, because we are considering classical particles. And it is particularly interesting to take this limit, but keep the ratio between h bar and g constant. And this is because in this way, we are losing the Planck length as a reference scale, but we still have an energy scale, the Planck energy. So basically, at the moment, we are going along this path in such a way that we are not losing also the Planck energy scale, okay? Otherwise, we lose both, and there is nothing left to see, right? So because we have only one energy scale and not a length scale, then we should expect that if there is any residual effect of our quantum gravity effective model in this limit, then the best place to look is at the energy momentum of the particles, okay? Because it may be deformed using a dimensional scale. The space-time, we lost the scale to deform space-time itself, okay? And indeed, if we do this limit, well, space-time becomes commutative again. However, the phase space is still deformed. Okay, so you're just doing the usual limit from commutator to Poisson brackets, the same one that you do in when going from quantum mechanics to dynamical systems, okay? And you're left with commutative objects with non-trivial Poisson brackets. And the one between time and space, knows about what was the commutator we started from. But then we also have a deformation, for example, of the relation between time and momentum. So here you would usually have 0 in a standard classical phase space picture. So this is the phase space of a free particle.
Excuse me, Giulia.
Yes.
There's a question in the chat.
Okay.
The person would like to ask the question. Maybe I can read it for you, right? So they're asking about what's the deformation that's leading to Poincare algebra in the
okay, let me read it. Which one are you reading?
The last one. So
how do you get to the specific deformation of the Poincare algebra? That was it, right?
Yeah, that's right.
I'm assuming you could deform it in various ways. This is the only deformation that works. So as I was saying, this deformation is the one for which this specific non-commutative spacetime is covariant. Okay, so you want to be describing the symmetries of your spacetime and the symmetries of whatever lives on this spacetime. So if I start from here, and this is, as I said, an assumption, is an example. There is no specific reason to pick this option. But then if I pick this option, then the symmetries of this spacetime are given by this algebra, okay? There is a little bit of a caveat here, meaning that since we are in a Hopf algebra rather than a Lie algebra, then we can change a basis for the generators. In Lie algebra, the change of basis has to be linear, a linear combination of generators. Here it can be non-linear, and you would still be within Hopf algebra. And changing the basis has consequences for the actual, for example, kinematics that you get. Okay, so there is a little bit of wiggle room here. But at the moment, there is no specific reason nor for choosing a specific non-commutative spacetime, nor for choosing a specific basis to describe the symmetries of the spacetime. If we had to measure eventually something, then we would have indication about what is preferable. But at the moment, we are using this as a way to construct possible effects. And as you will see tomorrow, since in the end, we will only be concerned with the effects that are relevant at the first order in the deviation from the standard theory, many different models end up being equivalent from that point of view, okay? So it's not that radically important. I mean, if you change the non-commutativity model, well, yes, you do see, I mean, you do see differences, but you do not see as many as you would if you had access to the full scale, okay? I don't know if there was another question since we stopped.
It was not a question, but I was curious exactly about what you explained, that if I modify the algebra, then I'm thinking that affects how boosts or rotation looks like in my spacetime. So if I were to maybe guess what that looks like phenomenologically, would it be like Lorentz invariance violations or something along this line?
We will get there tomorrow. I don't want to, I mean, today I want more to focus on examples of modeling. And then tomorrow I will make this link. So, I mean, it's a long answer. So if you don't mind waiting, we can discuss it tomorrow.
Yeah.
Okay, let me move on. Okay, then you have your phase space, then things become quite standard, even though you have deformed relations, because then you know, for example, how your symmetry generators act on the phase space. They act as usual via Poisson brackets. So the formalism at this point is quite trivial. Of course, you will get that the transformation rules are different with respect to the ones of special relativity because you have this deformation. And one thing you can do, for example, is to look at, take the Casimir of your algebra. So you see it is a nonlinear deformation of what we usually have. The Casimir is the mass invariance of the, in this context, in the context of a free particle. So you get that the relation between energy and momentum of a particle are deformed with respect to special relativity. And here I am also writing the first order effect, meaning the effect with the lowest power of energy over the Planck energy, okay? And to give you an idea, here is a plot of energy versus spatial momentum. you see that for very small energy momenta, the relation resembles the one of special relativity, but then you get this behavior, and in particular, for the case of a massless particle, say for a photon, you get that you're only allowed photons with up to Planck scale momentum, okay? And then from, as I mentioned, besides the non-trivial commutator, you also have these other non-trivial structures. And in particular, I mentioned that the coproduct tells you about multiparticle states. And within this kinematical model, it means that it tells you what is the law of addition of energy and momentum when you have an interaction vertex. And in this specific model that we are considering, the deformation is in the addition rule for spatial momenta. So if you have momentum P1 and Q1, the addition takes this form. So you have an additional exponential factor here that is suppressed when, this EP, sorry, this is a bit of bad choice of notation, is not the Planck energy, is the energy of particle P. Apologies about that. So you see that you have a correction term that goes as the ratio between the particle P energy and the Planck scale. So for very small energies, this term is 1, and you get back to the usual addition rule. Otherwise, you have a correction. And here, one slide that wants to show you in which sense I'm saying that this kinematical theory that I am developing is a relativistic theory. So this is already starting to go in the direction of your question that I postponed. So the question is our kinematical model invariant under the deformed symmetries that we are considering? For example, we have that the action of a boost is deformed in this way, action of boost on energy and momentum. You see that the one on energy is the standard one, the one on momentum is deformed. For example, is the energy momentum dispersion relation, so the on-shell relation, invariant under the action of this boost? And you can verify that it is, because when you do the brackets, you get 0. This means that your relation between energy and momentum will be the same for all observers that are boosted according to this law, okay? So there is no preferred observer. Also, you may ask, are these laws of addition of energy and momentum covariant? Again, you want to verify whether there would be a preferred observer for which this is true and others for which it is not, or whether all observers would agree on these rules. And here things are a little bit more subtle, just because if you do it carefully, and this is something you can easily try to do yourself using just what is written in this slide, basically, you will see that the boost parameter receives a back reaction from the momenta. So the boost parameter that you apply to the second particle has a correction, an energy-dependent correction. But if you do this, then this is covariant. And you can also show, and this is shown, for example, in this last paper, that even with this slightly deformed way to boosting, there is no way of defining a preferred observer. So all observers will agree on these laws. And here I cannot go in details because we don't have time, but basically this fact can be traced back to the fact that also the boost generator has a non-trivial coproduct, okay? I forgot to say in the beginning, in the slides, I put references when I am referring to specific results. But then at the end of the course, I will give you a list of reading suggestions about more general issues and reviews. So the references that you see here are referring to specific results that I am mentioning. Okay, so we have a kinematical model that is deformed, but does not violate the relativity principle, okay? It's just that the ways different frames are connected is described by the deformation of the usual transformations. And a way to look at this, I am showing this because it will be also useful later. You can understand all of it as a manifestation of the fact that, in fact, the momentum space of your free particle has a non-trivial geometry. So in particular, for the kinematical model that I have been discussing so far, it turns out that the momentum space of the particle is a portion of a de Sitter manifold. And the curvature of this de Sitter manifold is given exactly by the deformation scale kappa, so by the Planckian scale. I see that I am running a bit late with time, so I'm not going to discuss the details of this. I'm just going to mention, then you can check out the slides if you are interested in learning more. I just want to say that in this perspective, the relativistic properties, so the fact that the model is relativistically invariant properties, can be seen from the fact that the line element of the de Sitter manifold in momentum space is invariant under the action of the boost that we described before. Yeah, I'm not going to mention this last part. I'm not going to mention that, but I want to mention two last things again to show that because we are in a relativistic model, even though deformed, we should expect deformations of standard facts of special relativity. One example is the fact that you know that in special relativity you have relativity of simultaneity because the speed of light is finite and invariant. Now you see that in this theory we are deforming, basically here we are deforming the boosts in this specific model that I am considering. And they are deformed in such a way that the Planck energy is another invariant of the theory. And you can see it from here, for example, it appears as the maximum scale of momentum, but you can also try to boost a momentum of Planckian size, and you will see that it is unchanged. In the same way as if you boost in special relativity a velocity equal to the speed of light, it will not change, okay? So we have a second relativistic invariant. And this means that we should expect something else to become relative in the same way as invariance of the speed of light led to relativity of simultaneity. And in fact, what is found is that it is the concept of locality that becomes relevant. And this led to all a line of research about relativity of locality. Here, I don't want to go into the details, but it is interesting to consider this fact that within these models, interactions are local only from the point of view of an observer that is local to the interaction itself, while a faraway observer or a very boosted observer would see the interaction as slightly non-local, okay? And this is relevant also when we want to make connections, for example, to field theories. So this is why one of the reasons why it is hard to build a field theory on top of this kind of models, because we know that we need to modify locality, not in a radical way. So it's not that the theory is non-local, but is local only for observers that are close to the interactions. Okay. And another feature that one can study, for example, is how time dilation changes within these models. And again, within the model that I'm using as an example, you can in fact define a space-time metric. You want it to be covariant, of course, and you can define a covariant space-time metric, covariant under the deformed symmetries. You see that it is energy dependent. So it is basically the metric seen by a particle of a given energy, roughly speaking. And using this, you can compute, for example, the effect of time dilation. That is a very standard computation in special relativity. And you will see that you can still write time dilation in the standard form, so through some gamma factor. However, the gamma factor has a slight different dependence on the mass and the energy of the particle that is being boosted. Okay. This one at the moment is not an example of something we may hope to see, because if you put in the numbers, the difference is very small between the standard scenario and this deformed scenario. However, I find it interesting to look at how the standard features of a theory change within the new model. So I just thought it was interesting to mention. Okay, so now I don't have very much time left, I think, but I will start discussing the other way, another possibility for modeling properties of quantum spacetime. And I will stop when time is over, and I can continue tomorrow. So here now we are going in a very different setting, even though at some point I will discuss possible relations with what I've been saying so far. And here is an example. Well, also before we were introducing noncommutativity to describe limitations in the localizability of space-time point that we have reasons to expect in quantum gravity. Here we don't start from some general expectation coming from general arguments about quantum mechanics and general relativity, but we are starting from a collection of results coming from different quantum gravity theories. And in particular, between, say, 10 and 20 years ago, people working in different approaches started to look at the space-time dimension. Well, I'm going to define space-time dimension in a second. They started looking at how space-time dimension would change when changing the scale at which you were looking at it. And in different theories, they were finding that while you have, as we see experimentally, four space-time dimensions at large scales, meaning human scales, then when you go to very short scales, so in the UV limit, you have a different number of dimensions. And this was a result that was appearing in within different approaches. So it is interesting from the point of view of phenomenologist. I see something recurring from many theories. Then I wonder, okay, let's see where this can go, because it's something interesting. Okay, it has a interesting theoretical ground. So let's see if I can do something with it. So first of all, what were people actually looking at when they were saying that there was running of dimension? They were looking at spectral dimension. So basically, they were considering a diffusion process in space-time. Space-time turned Euclidean, because the diffusion process is defined on Riemannian manifolds, okay? And when you have a diffusion process, then you can define what is the probability that after some diffusion time, you come back to where you came from. And this is the return probability. From the return, and it is known that the return probability is related to the dimensionality of the manifold. And in particular, the limit for zero diffusion time of the return probability gives you the dimension of the manifold that you're studying. This is something standard for in smooth manifolds, let's say. For example, in a flat space with d dimensions, you compute the spectral dimension and you get that it is d, which is what you started from. And in particular, for flat space, you have no running. So for any value of the diffusion time, you get always the answer d. Let's say that the diffusion time tells you what is the scale that you're probing. So short diffusion time, you're probing short scales. Large diffusion time, you're probing large scales. When you have curved manifolds, the spectral dimension can be used to test curvature. It's related to the curvature invariance of the manifold. And in the limit of zero diffusion time, so when you're looking at the manifold locally, when it is practically flat, then you get again the answer d, okay, which is the dimensions you started with. So people had the idea of using this concept to test the dimensionality of quantum models of spacetime, okay? And as I was saying, in different models, they were finding that the dimension was running. So for small diffusion times, meaning at small scales, people were finding a different number of dimensions than the ones they had in the large scale. And in particular, interestingly, several models were finding a running to 2 dimensions. Say you start from the usual number 4, and then you go to 2 dimensions. So one starts wondering, okay, what can I do with it? And there are some interesting observations. One is that the running of the spectral dimension can be understood as due to the fact that instead of having the deformed space-time that you have a smooth space-time, but you put a deformed Laplacian on your theory. So this would be an equivalent description in the sense that it would give you the same running of the dimension. And this can be easily understood because in your Laplacian, if you're deforming the Laplacian, then you get a modified solution for your diffusion equation. When you put this in your return probability, you will get the spectral dimension, the running of the spectral dimension. And by adjusting the function that is modifying your Laplacian, you can reproduce different runnings of the spectral dimension, okay? And when you go to the Fourier space, basically you're saying that you are considering a deformation of the dispersion relation of your Fourier modes, okay? So one question could be, does this mean that in some sense, these theories that find the running of the spectral dimension can be also described, at least for some of the scopes that we're interested in, as theories with a deformation of the momentum space dispersion relation? Here is an example, which I'm not going to go into the detail. It's just one example of a dispersion relation and how it generates a running. And depending on how you deform the dispersion relation, you get a different running. Then I think I have 5 more minutes and then I'm done. Is that okay, or should we stop here?
As you wish. Maybe it's a good place to stop because you're going to say something new, or
I was going to finish this discussion.
Go
However,
ahead. Yes,
it
please.
is true that tomorrow I will start from things that I'm going to discuss, so that I can also start a bit earlier.
Sure, please go ahead. Yeah.
Okay, just last few minutes. Okay, then once we understand that a deformation in the dispersion relation can generate the kind of running of spectral dimension, then we wonder what happens if we also change the geometry of our momentum space, in this case, our Fourier space, okay? And we find that also the geometry of the Fourier space, of course, affects the spectral dimension. So again, the question is whether one could have a mapping between these theories and theories with a non-trivial geometry of the Fourier space. Another question that one may ask is there anything else that this effective dimensionality can tell me? And for example, you can look at thermodynamics, because you know that thermodynamics depends on the dimensionality of the space-time where your gas lives. And in fact, what you find is that if you take your modified geometry of the Fourier space and your modified Laplacian, and you use the same modifications to describe the kinematical properties of a gas in four-dimensional spacetime, okay, you effectively get a thermodynamical behavior that is the one that a standard gas would have in a different number of dimensions. So in some sense, you can define a thermal concept of dimension that basically uses the relation, the Stefan-Boltzmann relation and the equation of state to define an effective dimensionality. But now it is based on thermodynamical properties. So it goes in the direction of something one can apply to some real situation, okay? And then let me close it here. This one, I will discuss it tomorrow. So the summary of this part, well, this second part, as you see, was less rigorous in some way. This is because it is something more new with respect to the non-commutative space-time model that we have been discussing earlier. It is something more recent, so many things are still to be understood. However, I wanted to give you an idea about what one can do when one sees some features and wants to use them for the purposes of phenomenology. So here, what we have seen is that we have this running of spectral dimension, then we can link it, at least in some cases, to an effective deformation, say, of the properties of the momentum space of the theory. But then once we have a deformation of the momentum space of the theory, then there are a number of things that we know that can happen phenomenologically. So we can wonder whether we should expect these things from any quantum gravity model that is showing that kind of running in the spectral dimension, okay? And on the other hand, one can also do the converse. If one has this link established in a robust way, then one can use established properties, observationally established properties about the momentum space to go back and see which of the theories is capable of reproducing the appropriate, say, running of the spectral dimension, okay? And I think this is a good way to stop now for today. So as just a preview of the next lectures. So today it was more about the modeling and the connection to the fundamental theories. Tomorrow it is going to be more about what physical frameworks are relevant to test different quantum spacetime models, and in particular, I will talk about astrophysics and cosmology. I will say something more about relativistic symmetries. On the one hand, because it is something that it is relatively easy to test, and on the other hand, because it is something that can help in selecting quantum gravity theories. Okay, so it is relevant on the two sides, and often there is confusion here, so I think it's important to discuss it a bit more in depth. And I will use that as an excuse also to give you an example about what does someone working on phenomenology do once, say, an experimental positive result appears. Okay, that would be just a thought experiment because we don't have any positive results. But it is interesting I think for you it is instructive to see how one would think in that case. And then towards the end of this mini course, I want to say something about the relevance of quantum system and tabletop experiments in quantum gravity research. I know that you had already a full course on quantum aspects of quantum gravity research. Here, the focus will be more on what is testable and what we want to learn from experiments. And okay, I stop here, and I'm happy to take more questions if there are any.
Thank you, Giulia.